So today's and tomorrow's class we are going to change gears a little bit. I mean, looking at topics that are sort of up and coming and but still related to the foundations that you have seen, foundations of distributed algorithms. Okay, so one, obviously everybody will attest to this, that big data is obviously one of the like popular themes today, right? Everybody works probably in one aspect of big data or the other, okay, or at least people like to say that I work. They connect whatever they do, they connect it with big data because it helps them. So today we are going to look at distributed big data. That means distributed algorithms for big data. So it is not a sort of a fake connection, but a very real connection. So distributed algorithms and big data, they go together very well. I mean, there are different aspects of big data people are studying. For example, people can look at machine learning for big data, mining big data, and so on and so forth. Here we are looking at an orthogonal aspect, right, which is how do you do distributed computation, okay, because in a sense I think that is probably one of the key aspects, if not the key aspect of computing with big data, okay. So the main philosophy in big data is that, at least one of the main philosophies is that we are really talking about really big data, okay. That means data that cannot fit into one machine, okay. So data is so big that you cannot load all the data in your main memory in one laptop and do some computation. If you can do that, that's still many data that people say big data can be done like that. I mean, because our laptops have become so, some of the laptops, some of the higher end laptops, they have like even terabyte of memory probably, and so you can do it at least external. So you can practically you can still run them, but if the data keeps growing, there's always going to be some limit, okay. So at least theoretically, that's we are not interested in that scenario, okay. So the theoretically the scenario that big data computations model is are those situations where the data is so large. Like for example, a very good example is the web graph, okay. So the web graph is so huge, I think maybe it's now clearly easily billions of nodes, okay. So what is the node in the web graph? Each node is the web page, and there is a link from one web page to the other if there is hyperlink, okay. So this is the graph that Google uses to do all the things. I mean, it's the main data structure that Google uses to earn its whole money, okay. So search, everything, it's happening on this web graph, okay. So it's so big, so billions of nodes and trillions of edges, and it does a lot of processing on that. I mean, computing page ranks and whatnot, okay. So it's so huge that you cannot really try to do any, I mean, even if you can fit it, that's another aspect. I mean, it's so, I mean, the computation will be so slowed down, okay. So that's really the aspects. So even if the data can be fitted into the machine, it's still sequentially computing data is too costly. So you want to partition the data across many machines and then jointly compute the thing. So that is the whole philosophy of distributed computation, okay. So big companies like Google, Facebook, and not even so many companies that are, I mean, even many companies that are not like common knowledge like Google, Facebook, many even smaller companies that you have never heard of, they have now clusters of machines doing computation on that data, okay. That's what people call now data analytics and things like that, okay. So really we want to understand how one can do computation on large scale data in a distributed way. That's what we are going to study, okay. So we are going to study more theory for it, but it's not like many of the distributed algorithms that we have seen till now. It's not difficult to take these algorithms and try and implement them. In fact, these algorithms I like more because they are much more amenable to implementation than some of the algorithms that I have seen before. Just for the simple fact that like we have seen MST algorithms and things like that. To really implement them, I mean, you can simulate them, but if you want to really implement them, you have to really implement them on a communication network. I mean, you have to get hold of a network. I mean, there are such network simulators that you can do, but it's not like programming your sorting algorithm, studying the performance of a sorting algorithm in your laptop. It's not as simple as like that when implementing distributed algorithms, okay. but these algorithms are somewhat more amenable. Okay, so you can take many of the software packages that are available like MPI or Spark, Hadoop, all those things, and you can implement them and study them basically. Okay, so since we are interested in theory, we want to study the theory for this and try to again see how you can design good algorithms. Okay, rather than just willy-nilly design algorithms. Okay, so there are two things I am going to talk about today. I would say that two important models I would say that capture that captures distributed computing on big data. Okay, so two are probably the important models today, and one is the MapReduce model. Okay, we are going to see that, and the second is I would say the K-machine model. Okay. So the MapReduce model is the model that models the MapReduce computation. That's popularly people say it Hadoop and all. I mean, I've written a Hadoop job and whatever. Okay, so but we are going to see the theory behind it. Okay, so there's no well-established theory. Okay, similarly, the K-machine model is a model. We'll see why this model is more suitable for, especially graph computations, but even for, I would say it's even a better model to capture generally distributed computation on large data. Okay, especially large graph data. Okay, than MapReduce. Okay, but historically MapReduce was the first model. Okay, so so MapReduce model was introduced sometime in 2010. Okay, so so this model was introduced in 2015. So I was also part of this model. Okay, so I'm a little bit going to talk about my own model, but it's now getting more and more adapted by other people. Okay, so we'll see why this model is better and what it captures, but first let's understand MapReduce model, which is somewhat more well established because it's been there for a while, and also although the popularity of MapReduce is sort of waning, I would say, in the sense like I heard that Google is using less of MapReduce and more of more of what I will call this message passing kind of distributed computation. I will come to that in a second, and that's what this model captures, the K-machine model. Okay, but let's first understand MapReduce model, and of course MapReduce was popular, still popular, but it was really popular a few years back. I mean, like, okay, it was sort of the de facto standard for doing large scale computing. Okay, so what is the MapReduce model? So as you know, I mean, if you have done like this kind of Hadoop code and things like that, so MapReduce basically is just an abstraction for, I'm going to abstract out a process of doing parallel computing. Okay, so that is one of the probably the main contribution of MapReduce. Okay, so it's a parallel computing model, but it's such a simplified parallel computing model. I don't know, you've seen other parallel computing models like what? PRAM, good, PRAM, right? But this is a much simplified model. Okay, and that's why it is arguably easier to implement, and that's why, I mean, it won many awards. I mean, the inventors of MapReduce, they won many awards. It was two people at Google. Okay, so so it's much simpler, but you can show that it's generally, it has essentially the same power as if you take enough rounds, it has the same power as the PRAM model. Okay, but it's much simpler, so you can easy to program. Okay, so why it's so simple? Because it has basically only three operations, but essentially two operations. One is completely sort of transparent to the user: map, shuffle, and reduce. Okay, so what are these operations? So so you can think of a MapReduce algorithm as going in rounds. Okay, and each round has these three phases, one after the other. Okay, the three consecutive phases: map, shuffle, reduce, and then map, shuffle, reduce, and so on. Okay, so what is a map operation? So map operation is nothing but it's an operation. It's a very simple. It has a very simple sort of API or input-output relationship. Okay, it takes a bunch of it takes an input, which is basically always, you can characterize them as key value pairs. Okay, so it takes a list of key value pairs. Okay, so basically tuples. Okay, so map basically so let's focus on, okay, So, I am going to talk about MapReduce. So, map, so basically it takes a list of key value pairs as input, okay. Okay. So, it is a you can think of it as a function, it is a function that takes a list of, or rather a mapping, it takes a list of key value pairs and outputs another list of key value pairs, okay, some other list, okay. Okay, these can be multi sets, meaning that they can be the same, I mean it is not, they are not, so you can think of them as a list, so there can be duplicates, okay. So, it is not really a set, it is a multi set, okay. So, a map takes a multi set of key value pairs and outputs a multi set of key value pairs, some other multi set hopefully, maybe it can be the same, but it probably changes some things, okay, right. And yeah, single key you can have different values, you can probably have even the same pair repeated.
Same key multiple times.
Yeah, you can have same key multiple times, same key multiple times, same one key multiple values and so on, okay, in this output.
So why are we specifying key and value? We could have just said it's a multi-set
Of no, so it is, that's why it is always like that. So, the formal not the formal, I would say when MapReduce was originally defined as a programming model, it was defined like that, okay. So, it is very easy, of course you can cast anything as a key thing, right, key value. For example, I mean you can if you want to input a graph, a trivial way is just put key as a dummy key and just put everything in the graph. So, you can, so I mean sort of you can ignore that, but generally we use the key value in a specific way, I will come to that in a second, okay. So I mean meaning that it doesn't lose generality, okay. So, you can basically encode anything as a key value pair, okay. So, so that is the map phase. What is the shuffle phase, okay. So, the shuffle is nothing but it moves the, so the shuffle takes the output of the map phase, that is these key value pairs, and sort of routes it to machines, okay. So, map, of course map phase is done by machines again, but they are called mappers, okay. Mappers are machines, they are the same machine, I mean it is not, generally people use mappers, refer to the machines as mappers when they are doing the map phase, and of course the same machines might be doing the reduce phase, so then they are called reducers, okay. So, during the map phase the mappers compute something, they have this list output of key value pairs, and the shuffle phase routes these key value pairs to other machines, okay. They are called reducers, it can be the same machines but some other machines, okay. And the reducers, so it basically this routes, okay. So, it routes these key value pairs, okay. Okay, these are all a pair, not one, that can be list, okay. It's a list basically, so list, okay. So, it routes these lists, okay, I will put it as a list to machines in a certain way, we will come to that, okay. We will always, there is a way to route that, okay, come to that in a second, but it does this routing. And what does reduce phase do? So, it reduces to the machines, so these machines, and machines are the reducers, so okay, it routes it to the reducers, which again they take a list of key value pairs, basically these pairs, okay. So, that is why this is completely transparent, so many times we just completely omit it. When we come to designing algorithms, we will see how we explicitly state them algorithmically, okay. So, it takes these key value pairs and then returns again a multi-set of some other, maybe key double dash value pairs, okay. And this again, this will end one round, and this will be the input for the map phase for the next round. So, these will be these again, so these machines themselves will send it. So, the reducers will do this computation, reduce it, so this is called the reduction step, okay. So, it will reduce it, and this will be automatically routed to the machines for the next, to the mappers of the next step, and the process continues, okay. So, that is basically the computation model, okay. Okay, it is a very simplified computation model. So, why it was defined like this was because I completely have to, so even shuffle phase I sort of, we will see that the shuffle phase is sort of transparent to the programmer or the system or the algorithm designer. So you only has to write the code for this and this, and that's why, that's one of the reasons why Hadoop and MapReduce have been very successful, because I just have to write a code for map and code for reduce and then just feed it. Okay, there's one important thing that is sort of not probably obvious here, but it's implicit in the way I define these operations. These map phase, of course the reduce phase, but especially the map phase, it's completely stateless, and that's very important. So they are stateless. So all these are stateless. What do you mean stateless? So every time I'm getting a list of key value pairs and just operate on that. I don't, so map machines don't remember what happened previously. Okay, so what is the big advantage of being stateless? Yeah, so you can just schedule the key value pairs independently, right? So there can be as many mappers as possible. Whenever I have a key value pair, I send it to some mapper. So I don't have to worry about, I have to send this particular key value to that machine because that machine remembered something about it and so on. So that is why I get really, if something is really parallelizable, this really works. Okay, so that's the big success of MapReduce. Okay, so that's why it was developed by Google. They add this very nice thing of abstracting out. Otherwise, it's not a big thing. It's already, it's another parallel model. Okay, one more thing that is all typically used. Okay, so one of the properties of MapReduce is that, so this mapping is there, but when you do the shuffle phase, this routing, what happens is, it's not, these key value pairs are not generally routed to arbitrary machines. It's always routed with the following property. So all the key value pairs with the same key are routed to the same machine. Okay, so that is the property, that's another, you can put it as part of the model. Okay, so you have list of these key value pairs. Okay, of course if there is only one unique key, then of course there is only one unique key, but that in the list of key value pairs, there can be many pairs with the same key. All of them will go to the same machine. The shuffle automatically takes care of that. The shuffle is transparent, it makes sure that all the pairs with the same key value are routed to the same reducer. Okay, so basically, so this is the, so all of them, let's say if there is pairs which are, let's say k1, let's say this is value 1, k1 value 5, k1 value 10. Okay, and maybe there are other pairs in the list. Okay, maybe k2 value 2, k2 value 1. Okay, so you have a list of these, let's say these 5 pairs which are the output of the map step. The shuffle will do what? It will reduce these, it will route these two to one machine, let's say M1, okay, and route all these K1 pairs to machine M2.
M1 can be equal to M2.
M1 can be equal to M2, that's fine, that's true, but they should go to the same machine. Okay, of course, the point is they are so large that there will be many machines, these. Okay. So that is the model. It's a very simple model, and to understand this, probably let's look at a very simple algorithm, where this is sort of usually the first algorithm that people sort of give to understand the thing from MapReduce. Okay, and that is what is called, let's say, and this is one of the first applications I think that probably motivated Google, right? So Google, let's say they want it. So when you do a search, you want to, let's say you are searching for a word, what Google does, it lists all the web pages that word has, right? That's one of the basic things it does. So obviously Google designers, so the guys who developed it, I think they won a lot of awards. I think it's Jeffrey Dean and Sanjay Gamawat. Okay, so they were looking at this, and when the web pages, there are not too many web pages, it's probably easy to do it in a few machines, but as the web grows, you have to basically process not just the web graph, but every document in the web. You have to process every web page. Okay. So, you have to read every word in the web page and you have to sort of reverse index it. Okay. So, let us say you want to count the number of words in every document. So, you have a bunch of documents, maybe all the web pages in the world in the web, and you want to count the how many times a word occurs in every document, or overall or a bunch of documents. Okay, you are given a bunch of documents. You want to list all the words in all the documents and the total sum, that is the number of times it occurs in all the documents. Okay, so you can write a easy MapReduce algorithm for this. So what will the MapReduce algorithm look like? So you can write a MapReduce. Let's say so the map will take as an input that is, let's say, okay. So maybe a list of, so this is the input, this is actually a list, think of that. So it's a list of all the documents, the document ID and the document itself. Okay, so it's a list of all the documents. So I want to count all the words in maybe bunch of million documents. So that's the list. Okay, so and it's going to take a list and emit a list and output a list. What will be the list? So it's going to do that. So for all, okay, so for all words, okay, so for all words in this, what it's going to do? It's just going to output, it's going to output a pair. Okay, so it's a very simple pair in this case. It's going to output this pair. Okay, so it's going to look at all, it's going to just, so this is a very dummy thing, right? It's going to just read it's going to read each document, and in each document it's going to read every word. For every word it's going to output this pair, the word and one, basically means that word occurred one time. Okay, that's it. So it's a very simple mapper. So it maps words to one. Okay, so this is a huge list of key value pairs. That's the mapper. So what should the reducer do? Of course, the shuffle is transparent. That means what? It will reduce, it will route all the words which are the same to one machine. So what will it do? So let me look at reduce now. So I want to reduce the reduce code. So it will take what? It will take a list of pairs. Okay, so maybe I should say like this. It's a list actually. So it's a list of pairs W and what? So let me write this. So it will be a count. Okay, so it will be a list of counts. So let me write this like this. That means what? It will take pairs like W comma C1, W comma C2 and all. Okay, so of course these C1, C2 might be just one. Okay, so it takes W1, W1, W1 for many ones. Okay, and what it will do? Yeah, so it will so maybe initialize sum equals 0. Okay, for okay. So and then finally it will output W sum. It will output that pair. Okay. So the reducer simply adds all the. So I have written generally C, but sometimes it can be generally C, but it's usually 1. In this case, it's just 1. Why? Because the whole, and how many rounds does it take? 1 round, because there's one map and one, just so that's why it's very efficient. So that's why for such jobs MapReduce is still the way to do. I mean, if you want to do this kind of job. Okay, so MapReduce you will see turns out to be not so efficient when you want to do many rounds, because every time you are doing this, what is sort of the complexity of this kind of a model? What is the complexity of computing in MapReduce? What is the sort of the bottleneck? Yeah, shuffle phase, because that's because as I told you, that principle is very much underlies the principle that we have been seeing all along. So the map computation and reduced computation are local computation, they are within machine computation, they are significantly cheaper. So the real costly operation in MapReduce is really the shuffling phase. So because you have to move all these pairs to the reduced machines. In fact, this can take days actually. I think maybe to do the web page computation it will take one round, but just moving this data is so thing. I mean that is the costly operation, just moving them. Okay, so even the bandwidths are so high speed links, but these data are petabytes data. So I mean they are just moving all the pairs. So you want to really minimize the number of communication rounds. Okay, so MapReduce is really good when you solve problems in like essentially constant number of rounds, and it's reasonable. Okay, and many problems are like that. You can solve in constant number of rounds. We'll see one more problem. Okay, but there are lots of problems, especially in the graph domain, where it's not clear whether, let's say even connectivity. I mean it's not clear. So there's a very famous open problem in MapReduce is that it's not clear whether you can solve connectivity in less than log n rounds. So there's a very easy connectivity algorithm that you can solve in log n rounds, but already log n is too much. Okay, so there MapReduce is not suitable. Then you have to use the K machine model. Okay, we'll see why that's a better model inherently. Okay, but let's go and do one more non-trivial thing. Okay, so this is the very like toy thing. So let's do a real problem. Okay, so let's look at the problem that you have seen a lot. I mean this is sort of the touchstone. In fact, it's a graph problem. Okay, so maybe before that let's go to even a slightly, just to get used to MapReduce way of thinking. So let's look at, for example, I'm given a graph, okay, and I want to, let's say, compute the degree of all the nodes. Okay, so what is the input for this problem? Again, you can think of it as the input. You can always think of it as a list of key value pairs. Okay, so you can think of the input as the list of edges. Okay, so maybe just an edge and maybe one or something like that, because it's always to be a pair, right? So because you can say, so e1 1, because you can, if the value can be dummy, for example, right? So that's why you can encode anything. So the value can be dummy. Okay, or maybe it can just say the value just can be the graph ID or something like that. So if you look at one graph, that ID will be the same. So that doesn't give you anything. Okay, so you can take the input as a list of pairs, edge pairs, and the output should be a list of pairs again, where the first key will be the node ID and its degree. Okay. So this is basically like the count problem we saw, but it's a count problem in the graph setting. Okay, so I want to compute the degrees of all the vertices. Okay, so the input is a list of pairs. Okay, list of edge pairs. Okay, list of edges list of edges, and the output is again list of pairs, where it's basically the so ID of the vertex, ID v, and its degree v. Okay, it's a list for all the vertices. Okay, that's the computation. Okay, so how can I do this using MapReduce? I claim that I can do it in basically one round. Yeah, right. Yeah, same thing basically. So this is just using the word count thing to do the thing. Okay, so that's it. So I'm just translating that to the word problem. Okay, so this is just I can do a one round. So why I'm saying it like that? Why I'm saying this? Because I'm going to look at a non-trivial graph problem, MST. So sometimes when we design algorithms for MapReduce, we don't even go to the level of map and reduce. Okay, we operate basically, we give a code at the machine level. We are even little bit more abstract, because the low details can be implemented like this. So for example, I'll say compute the degrees, but I won't actually give a map and reduce thing for that. You can do it. Okay, so when you write pseudocode for MapReduce, it's better to think of not in the level of map and reduce, but at the level of machines. So machines do something, okay, and the shuffle automatically routes the thing. So, you always say machines. So, each phase can be can be thought of at the machine level. So, you write a code for machine and you say you give the input the input pairs for input value for the machine and output value for the machine. The output value is automatically routed to the some other set of machines which are the reducers. Okay. So, you do not exactly specify how it is routed, you can assume that there is this kind of a shuffle function that takes care of it. Okay. So, you only talk about in the terms of, you think of it in the writing code in terms of the machine level. Okay. So, of course, you typically only say the pseudo code for one round and of course, you iterate it. Okay. So, let us formalize a little bit, especially in especially with regard to a graph problem, because I am going to really look at graph problems today. Okay. Although I mean you can try to do big data for anything. So, I am specifically I am going to look at today big graph data, although it is not, okay, because it is in keeping with, you will see that is why I mean the connection to distributed algorithms, the kind of stuff that we have been seeing till now, there is a huge connection, there is a very close connection. Okay. So, let us look at, so right now I am going to look at our usual problem. I want to compute, I want to write a MapReduce algorithm for computing MST. Okay. That is my goal, but before that I want to really give a model. So, what the model I gave you, this MapReduce, is really a specification model. So, that is the model that the programmer kind of uses. So, yes, write map and reduce, but I have not really told you how to compute the complexity of it. Of course, the complexity is the number of rounds, but I did not say anything about I mean if I do not say any further, actually you can trivialize everything. I told you of course this will take one round, but if I do not say anything further about the execution model, you can say trivially I can solve any problem in one round. Why? Because you take the huge problem and then just you can encode a huge problem as just one key pair and just route it to one machine. Okay. That means route all the data, put just one key for all the data. Okay. And that will be routed to one machine and that will locally solve it, and that is it. So, everything can be solved in one round. So, that completely trivializes MapReduce, that does not capture what is happening in practice, that is not happening like that. Okay. So, what I mean, for example, in this word computation, I can put everything as one, all documents as one key, and then all documents come to one machine and that machine locally computes the thing, but that is like a central computation. Okay. So, of course, my complexity model does not disallow that. Okay. So, you need a complexity model that also captures what is happening in practice, that basically that non-trivializes the thing, this trivializes the thing. Okay. So, this is sort of the map thing I told you is sort of the specification model. So, I need a complexity or an execution model that sort of captures what is happening, that captures the big data. So, I have not told you what is the big data aspect of the model. So, why is it really big data? Okay. And that is this. So, basically I am going to assume that, let us say let us assume the size of the input is n, because I want to do complexity, obviously it has to depend on the size of the input. Here it is basically the list of the input key value pairs. Okay. For example, if it is a graph, it is a number of edges in the graph. So, if it is a huge graph, that is a lot. Okay. So, basically m is the size, number of edges. Okay. So, this is assumed to be very huge. So, I do not want to trivialize the problem by routing all the edges or the entire graph in one machine, then it is trivial. Okay. So, what is the constraint I should put to make this whole model non-trivial? So, I told you the main thing about big data is that I cannot fit the whole data in one machine. So, I have to put that constraint. Yeah, right. Yeah. So, even that, okay, I should not say n. So, even that is number of edges. Okay. So, this is n. Okay. Maybe I should not call it n. Do not think of n as a number of nodes. So, it's just the size of the input. In the graph, it's a number of edges, right? In other things, maybe I want to sort a bunch of things or whatever. Then it's a number of numbers or whatever. Okay. It can be. So, let me do not think of it. That's why I'm writing as big N. Okay. So, it's just the size of the input. Okay. In the graph setting, it might be a number of edges. Okay. So, the main thing we assume is a constraint on the memory of each machine. That is the main thing that makes the whole thing meaningful. Okay. So there is a constraint on the, so there is a bunch of machines, okay. I will come to that, but size of the memory is the most important thing. So there is a bunch of machine, right, these are both these, that is why I am going to talk only at the level of the machines. It can be a mapper or reducer or whatever, but whatever be the machine, whether it is a mapper or reducer, there is a constraint on the size of the memory of each machine. So we will always assume that this is sublinear, that is the thing that people are assuming. That means it is significantly smaller than this input size. That means I cannot fit the whole data in one machine, that is just impossible. Okay, so that immediately rules out this kind of trivial things like one round thing, it is not possible because I can't even fit everything, I can't route everything in one machine. Okay, so that means it is typically sublinear, so typically little o of n. Okay, then always, not typically, always little o of n, and also the number of machines is also sublinear. Of course, there should be one thing, right, the number of machines times the memory of one machine should be at least equal to the total size, because I have to fit the total thing somewhere, of course with that constraint. Okay, so still if you look at the number of machines, let us say the number of machines is k and this is the memory is m. Okay, of course k times m should be, otherwise I can't fit everything, right, in that thing, right. So I should be able to fit.
Point of time we should have some part of the input somewhere.
Yeah, otherwise yeah, that is true. So initially it is distributed somewhere, okay, but MapReduce algorithms, if you look at it, let us say I have an algorithm that terminates in constant number of rounds, okay, that means what, the algorithm has finished its job without any machine seeing the whole input, so there is not even time to see the whole input because it is seeing only little of n, it finishes in rounds. So no machine has saw the whole input, but still the computation has finished. Okay, that is the situation I am, that is why constant rounds make sense, or definitely very little rounds. Okay, so that is the idea. So you basically finish your job without any machine seeing the whole input. Okay, so we will come to a concrete example, but that is the computation model. Now what is the thing I have to reduce, what is the complexity now? Again it is the, given this constraint I want to reduce the number of rounds, that means each round is this 3 things which is transparent, because now I am talking about the machine level. Okay, so reduce the complexity is the number of communication rounds. You want to reduce this, ideally you want to be constant. Okay, so yeah, so again like local computation we ignore, it is polynomial, that means in each round the computation done by each machine is polynomial, but we sort of ignore it. Yeah,
I was just asking that.
Yeah.
That we are just taking memory, we are just considering memory in our complexity. What about the time? Because
correct,
map phase can generate a lot of
correct, right,
that can lead to a large amount of
correct. So that is, yeah, but that is going to not, we are not going to sort of counter that, we are not going to charge it to the computation, but we are going to charge it to memory. If it generates lot, then it is a problem, right, maybe it is taking too much thing. So in that sense indirectly we are restricting computation because too much memory is a problem, right, but generally it is going to be polynomial, we are not going, generally we do not assume like the distributed thing. I also said the local computation is free and typically we do not abuse it, that means we do not do non super polynomial, we generally do not do polynomial. In fact all the algorithms you have seen now they are very simple, at least especially in the Kanjas model they are very simple. Okay, so that means if you think about it, many of the algorithms that we have seen in the Kanjas model, if they have especially have very small local computation, you can translate them into PRAM models. So you can think of them, you can sort of translate them into PRAM algorithms, but not the other way around. The other way around is more complicated, but this is reasonably easy. Okay, of course if the local computations are very costly, then you cannot do that, because in PRAM local computation count, in one round of PRAM I can only do like small number of, maybe one step of the computation. Okay, Okay, now we are going to look at computing the MST. Okay, I want to come up with a MapReduce algorithm for computing the MST. So again, the graph is given as a list of edges, and I want to output at the end it will be a list of edges, but it will be the MST edges. Okay, the MST edges will be output. Okay, so what will be an algorithm? So again, I am going to look a little bit more abstract. I am going to write explicit, because it's, for example, some of these things might involve computing the degrees and all. So those are subroutines. So those are sort of, I am not going to talk about them. So I am going to assume them. Okay, so I am going to give you an algorithm that works, that finishes in constant number of rounds. Okay, but it does not come without assumptions. I am going to give you some assumptions on the graph itself. So let us say, so I am giving you an input graph. Okay, it is a weighted graph. Okay, so let me have some assumptions. So number of nodes is n. Okay, so number of edges is, we will assume it's called C dense. So this such a graph is called, so I am going to, the input is a C dense graph. That means the number of edges is slightly superlinear. Okay, so of course C can be 1, close to 1. Okay, so for sparse you have to do a slightly different kind of thing, but right now let us assume it's, so that means C is okay. So why this is a reasonable thing is, one of the reasons people study this is many real world large graphs like the web graph and all, it is sort of C dense. Okay, the C is like, I think it's some 0.1 or 0.2 or something. Okay, so they are slightly C dense graphs, the large graphs that you see in real world. Okay, they are not completely sparse, they are slightly super dense, slightly dense. Okay, so that is the thing. So now this is the input, right? Of course weights are there on the edges there, right? So I am going to do MST. Okay, okay, and of course by the memory constraint I am going to assume that the memory of each machine okay, so is what is, it has to be sublinear. So I am going to assume it is n to the 1 plus epsilon. Okay, but of course epsilon should be strictly smaller than C, so it is still sublinear. And I am going to assume, so it is important why I make this assumption. Okay, so where so it is definitely sublinear, but note that I am assuming not n to the epsilon, or I mean I am not assuming n to the 0.9, I am always assuming n to the 1 plus. Okay, it is very important to do that. Without that you can't get the kind of algorithms that I am getting constant. Why? What is the motivation for allowing this? So it is still sublinear, that means what? No machine can hold the entire, it non-trivializes the problem.
2 rounds it would hold the entire.
Not, I do not know about that, but maybe not be 2 rounds, we show we can give a constant round, but that is not the main, that is okay. So of course without that assumption I cannot, let us say I cannot say little of n here, that is also sublinear, right? But if I say that, that means what? No machine can even look at all, can hold all the nodes basically, that becomes very difficult. So it's still that's still open to get efficient algorithms in that model, so it becomes more difficult to do that. Okay, so it's not the easy algorithm that I'm going to tell you, but still it's a very nice algorithm. It's a very simple algorithm, but okay. So that means this allows each machine to hold all the nodes, because there are at least the n memory space, I can at least hold all the nodes but not all the edges. Of course if I hold all the edges it's trivial, I can just send it to that machine and it's one round. Okay, so I cannot hold all the edges. Okay, because this is strictly smaller than C. So think of C as like 0.2 or something, and epsilon is maybe 0.01. Okay, it is slightly, it might be slightly larger than 1. Okay, slightly larger one, like maybe 1.01. Okay, okay, that is the memory. So what is the number of machines? Of course the number of each memory times the thing should be at least the thing, right? So let us say the number of machines is eta. Okay, so eta should be, maybe let us say we can assume it is, without logical generality I can assume that it is let us say n to the 1 plus epsilon by C. Okay, Okay. So, this is n to the, okay, there are not too many, more than so many, you do not need more than so many machines. If you have more, then you ignore it because I am not going to use it, right, because intuitively I need to use only as many machines that as there are memory, right. So, since I have each machine has so much memory, I will always try to always use it fully because the whole point is memory, right. So, I will try to use, if a machine has some memory f, I am going to use all the memory, right, I am going to fill the bin sort of. After that I am going to ignore, if I have additional machines I do not care, okay, because if you have the memory, use the memory, okay. So, that is the model. So, in this model I want to give a constant round because generally that is where it is good. You can already see that MapReduce is good, but you can see there are a lot of assumptions here, okay. So, already for this does not work for sparse graphs and things like that, okay.
You need epsilon to be greater than 0. I mean, it doesn't suffice to hold all n vertices and maybe n edges.
No, I really need to be greater than, it cannot be 0. It cannot be 0. Let us see the thing. I think 0 means that number of rounds will be infinite, I think. So, yeah, okay, but let us let me given what is the good MapReduce algorithm in this. I want to come up with actually ideally I told you MapReduce algorithms are good only if they are constant round algorithms. Even super constant is not very good, at least definitely in practice, but of course theory it's good, but definitely not in practice, okay. So, and even for that is why we have to sort of, that is one reason, okay. So, this is people I am assuming super dense graphs, okay, and superlinear memory, superlinear in terms of n though, okay. So, let us look at an algorithm. So, let us think of a plausible algorithm for finding MST now. I am going to do MST. So, how will I solve MST? So, note that since I am shooting for like constant rounds, no machine would have seen the entire graph, but still they will be able to compute the MST, okay. So, what I can do? So, I am going to exploit a crucial property of the MST. It is actually a very simple algorithm. So, in fact, it is in some sense the obvious algorithm. What will I do? So, of course, what is the input? The input is a list of edges, okay. The graph is given as a list of edges. What should I do? So, I have some machines, okay. Initially, let us say at any point I will have enough machines to hold all the edges, okay. Initially it will be eta, okay. So, what I am going to do is, so the algorithm's idea is very simple. So, keep on pruning the number of edges, okay, in the graph, okay, till I have the number of the list of edges is small enough to fit into one machine and then solve the problem locally in one machine. That is it.
What is the expected output out of this?
The MST.
In what form?
It will be a list of, again it is a list of, in the MapReduce setting it will be, you can say MST, but it will be a list of edges, MST edges, 10 minus 1 edges.
All in just one machine?
Yeah, it does not matter, it is just emitted, so and maybe it is printed somewhere or whatever. So, different machines can emit different things, but here in this setting it can be the same machine, because that is where I have assumed that, that is why it is so crucial that I have assumed that one machine can hold superlinear memory, superlinear in number of nodes. So, one machine will presumably, so I think the algorithm that I am going to describe, the one machine, final machine which holds the thing will output the entire thing. So, it will print all the edges, okay. So, it will have that, it will have all the MST edges, it can hold that, okay. So, it becomes more complicated if you say that each machine has little of n memory, then different machines have to output different edges, okay. In the K machine model we will see that is what is going to happen, okay. That is more realistic and also for a different reason, we will come to that in a second, okay. So, but the idea is very simple. So, keep on, so the main technique I will say here is filtering, okay, main algorithmic technique, okay. So it's very natural thing, right? I keep on filtering the number of edges. Filtering is just pruning the number of edges, so that whenever I have a list of edges, in the second round I will have some other list of edges, the third round some other list of edges. Of course all these lists will be reduced by a large factor, okay, with the property that the MSE edges are still contained here. So the edges that I am pruning away are guaranteed to be not in the MST, okay, that is the only thing I need to do. So what will I do? So the algorithm is very simple, let me just describe it, okay. So I will always have some list of edges at some round, okay. Initially it is the entire list of edges. Initially I will have all the machines in my disposal, because I have so much machines, eta machines, okay, because that is enough to fit all the things. I am going to randomly, so the main algorithm is, it is a randomized algorithm, okay. So the main thing is a randomized algorithm. So it is going to randomly send each edge to a, so it picks a edge and sends it to a random machine. So every edge is assigned to a random machine, okay. And now once each machine gets its machines, what will it do? It will compute the minimum spanning tree or forest. Of course if it computes the minimum spanning tree, then it is done. If it computes n minus 1 edges, it is done, but in generally it might be a forest, okay. So how many, so initially I will have n to the 1 plus epsilon, okay. So they are sent randomly to different machines, eta machines, okay. So each edge is sent to one of the eta machines randomly, okay. So let us say this is M1, M2, M eta, okay. And what, so each will get exactly, so this is fine, right, because I know that since I have set up eta like that, each will get at most n to the 1 plus epsilon edges, that is fine, it still fits in the memory, okay. So what will it do? On that subgraph it will locally compute a MSF, a minimum spanning forest, okay. How will it do? Correct, it will just use the cycle property, just using the cycle property it will just remove all those edges are guaranteed to be not in the MST. That means you look at all the cycles, remove the heaviest edge in the cycle, in all the cycles in the graph, that is just a local thing. And how many edges it will output? Correct, it cannot be more than, yeah, it cannot be more than n minus 1. So each one will output n minus 1, okay. So how much I have reduced, what is the factor I have reduced the number of edge. So initially each machine had n to the 1 plus epsilon, and each machine has reduced by a factor of n to the epsilon, okay. Now what should I do the next thing? Reduce the number of machines. So I always take the number of machines to be the total number of edges divided by the memory, okay. So the number of machines L, so that is initially it was like this, so let us say number of machines okay, number of edges currently there, let us say number of edges in round I, okay, divided by the memory, because the number of each machine is right, okay, the total number of edges, okay. So this guarantees what? Every time the number of edges in each machine will be what? N to the 1 plus epsilon, because I am dividing by that, right, because that is the memory of each machine. Oh sorry, number of machines, sorry I should say, yeah, so that is right. So this is the number of machines, but this is the memory of each machine, okay. So this is number of machines, okay. So this is the memory of one machine. So every machine will get, in every round will get how many edges? N to the 1 plus epsilon, and it will reduce it to n minus 1. So in every round what is the factor reduction?
N to the power
n to the epsilon, and I am starting with n to the, so every time I am reducing by n to the epsilon, how many rounds it will take? Constant number of rounds, because every time I am reducing minus epsilon c over epsilon, c over epsilon is 1 plus c over epsilon, something like that. So constant number of rounds, because c and epsilon are constants. That's the algorithm, very simple. Okay. So this algorithm is used in Google. So the guys who came up with this algorithm is Google people. Okay. But I'll give you a better algorithm in the K machine model. Okay. But before that, but only what is the only thing that we have to analyze here? So this is guaranteed. When is this guaranteed? So I need one thing to guarantee this: the randomization step, because I just have to show that the randomization step is balanced, right? So because the point is the mapper does a very simple thing. I just said it abstractly. What does the mapper do? Just takes the edges and randomly sends it to different machines. So if the mapping is not balanced, then I don't get too much, because I want the mapping to be balanced. That means everybody gets n to the 1 plus epsilon, so there is a good reduction. Okay. So I just have to make sure that there is a good reduction.
If you do an arbitrary distribution of edges to machines, because anyways the spanning forest, the edges will be at most n minus 1.
That's true, that is true, but the point is I want to do this quickly though. So I really want to do this quickly in a way that that conforms to this. Okay, so maybe I did not say one thing. So one thing that okay, maybe this is something that you are right. So one thing that I forgot to say, and why this randomization comes naturally, is because this, if you look at, let's go back to the specification model that we saw before. Like there is this map, shuffle and reduce. Okay, the shuffle takes what it takes, the key value pairs with the same key, and routes it to the thing. Okay, so there can be multiple there can be lot of key value pairs, okay, with multiple same keys. Okay, so let's say key 1 bunch of pairs, key 2 bunch of pairs. So what it does is, it does not, in general, I don't know what the load is and all. Okay, so what it does is it basically hashes it. So each key is hashed to some machine. That means I use the hashing function. So we are going to assume that this hashing function is random. Okay. Because why is that? Because I want keys that are generated, same key that might be generated by different mappers, to go to the same thing. So there is no time to talk and coordinate and all. There is no time to talk and coordinate. So generally so I did not say that, but generally the thing is, this is done by hashing. So there is a hash function, a shared randomness. The hash function gives you shared randomness. That means what? It is random enough. So it is usually, the best way to do it is by, I mean, of course in practice you use a hash function, but it is theoretically the best way to do this is universal hashing. Use a universal hash function. That means what? It is hashed. That means if I take one key, there is a unique output, and it is done without any coordination, right? So the machines cannot coordinate and say this thing, I mean, let's agree that all the key values, all the values with the same key should go to this particular machine. There is no time to do that. There is no such facility in the model to do that. So it has to be done instantly. So the hashing is the beautiful way to do it. So I just take the hash it to the key and get the machine. So hash will give you the output of the machine ID. So I route it to that machine. So everybody is automatically routed it. Okay. So that's why I am using a random value. So the randomness also comes naturally. So everything is here hashed randomly, every edge. So here every edge is like, that's the key, that's one key for that. Okay, separate key, each edge is a separate key. Okay. So you just have to show that, so this is actually this is just a load balancing problem. So if you have, let's say, F items, and so I don't know whether you know balls and bins, you have seen balls and bins. So you have F balls, okay, and let's say you have G bins, okay. So there are G bins. Think of there are F balls. You have to throw the balls randomly in the bins. Assume that each ball is thrown randomly in the bins. That is exactly what is happening. The balls are the edges, the bins are the machines. Okay. So, one way to do that is, that is why I mean that is why I am not doing, or it is not very efficient to do what you are saying. For example, of course, if ideally I want load balancing, so it means I want approximately every bin to get F by G balls. So one way is to do it sequentially. So put the first F here, second F here. That needs coordination.
That requires a centralization.
Correct. That's why I don't do it. That's why I do hashing. It's very powerful. Randomization. So there's no coordination, but it gets you on average. What is the average? If I do, that means every ball is thrown to a random bin. So take a ball, throw to a random bin. That means every ball has a probability of 1 by G to go to a particular bin. So you don't see what's there in the bin, just throw it. So this is completely stateless. There's no coordination, nothing. Okay. What is the expectation? How many balls there? F by G. And you can also show that the I probability it will be F by G. For example, here in the very first step there are so many balls, n to the 1 plus c balls, number of bins is eta. Okay. There are eta machines. So what is, so eta is what? Eta is that. So that means n to the 1 plus c divided by this eta, which is n to the 1 plus c times n to the 1 plus epsilon, which is basically n to the 1 plus epsilon. So on the average I am perfect. That means I am going to get n to the 1 plus epsilon. But I don't want, but if the deviation is too much, then it's bad, right? Let's say one machine gets n to the 1 plus epsilon dash, where epsilon dash is slightly larger. That's not good. That means I cannot store so many edges. So that's a bad thing. But what I can show is that this is the expectation, because this is the F by G is the expectation, that's well concentrated. So I'm not going to do this, but it's very easy to show by Chernoff bound. That means what? With I probability, the number of edges in a bin, okay, is the number of edges in a bin being larger than, let's say, so the expectation is exactly 1 to the n to the 1 plus epsilon, the being greater than, let's say, twice that is very small. Let's say it's very small. You can easily show this by just using probability tail bounds.
It inherits the properties of the hashing function.
Correct. This is using, right now I am being a little bit more, I am just going to assume that it's a random hash function. That means it's completely random, but that's not quite true though. But you can simulate that. You can assume, for analysis we'll assume that it's basically throwing balls randomly. But that's why, but there's a slight technicality here. That's when we analyze, for simplicity we'll assume this. But if you really think about it, the hash function is not exactly random, because it's not really random, it's a deterministic function, right? But you can show that you can design hash functions such as universal hash functions that are essentially like random. Okay, so they have this big bound. Okay, but for analysis we'll just assume they are random. That means they are independent. Okay, but they are not independent, right? Because it's a function, so every key has to go to the same thing. It's like saying that balls of certain type will always go to the same bin. Okay, that's not true here in the balls case, but in the hashing case that's true. So it's not exactly random, it's a deterministic. The hash function is deterministic, it's a one function, but it has this property that if the items chosen are, so that's why it's called universal hashing. You have to use universal hashing. Okay, there's enough randomness there to get this property, but if for analysis we'll just think them as like independent. Okay.
So an edge is never assigned to two machines.
Yeah, only one machine. The only problem is that's clear, because I always send it to one machine by the hashing, but I don't want, so here also here one ball is always sent to one bin, but you don't want some bin to be overloaded. For example, some machine to get number of edges which is much larger than the memory, because the memory is fixed to be like, I won't say it's n to the epsilon, but I mean I should say it, so I should O of n to the epsilon, right? So what I am showing is, since if I fix the memory to be 2n and 1 to the epsilon, with I probability there will be no violation. There will be no violation. Okay, so that slack is given by the loss in randomness. You can show that slack. It's not a big deal. So this is the algorithm for map, for if you want to do MST in MapReduce. So this is the algorithm you will write in Hadoop. Okay. So, for the you have to still actually I am giving it as an abstract way, but you have to write the map and reduce steps explicitly. Okay. That is not difficult.